Hi. Recording in progress. Okay. So I'm Tony. I'm a research staff in Dr. Chapman's group, and I work with Shilei. Shilei's from Xi'an in China, or has somewhere around there. He's working on compiler and runtime optimizations for heterogeneous computing systems in high-performance computing. So systems with GPUs and similar devices. And in particular, he works on the OpenMP programming interface. And he's going to tell us all about the stuff he's done with the LLVM and Clang compilers to enable this to happen. Over to you.
All right, thank you, Tony. Let me share my screen. Let me know if you can see it.
Yeah.
All right, cool. Okay. So hi, I'm Shilei. I'm a PhD student in Dr. Barbara Chapman's group. And today I'm going to talk about efficient development and the execution of GPU programs, basically SPU's contribution to LLVM OpenMP. So before we dive into the details, let's first talk about the heterogeneous architecture. So if you look at the figure, this figure shows the theoretical peak performance between GPUs, AMD GPUs, NVIDIA GPUs, and Intel's Xeon processors. So you can see that no matter it is AMD GPU or NVIDIA GPU, there is always about an order of magnitude performance gap between them. So actually in recent years, especially after 2016, the gap is becoming larger. So almost all recent supercomputers have GPU. Actually, Fugaku is an exception. But from my perspective, the organization of those cores, the architecture of Fugaku, I think is pretty similar to a GPU, but it's pure host cores, CPU cores. So anyway, so this one is a Summit supercomputer. It's a last generation supercomputer in US. And in this generation supercomputer, we have three basically. Aurora is provided by Intel. It has Intel CPU and Intel GPU. Pearl Murder has AMD CPU and NVIDIA GPU. Frontier has AMD GPU and AMD CPU. So now we know that, okay, GPU is so cool, let's use it. But the first question is, how can we use it? Basically, what programming language should we use? Well, the answer is probably, it depends on what system you are going to use. So for Summit, it has NVIDIA GPU. So basically, the programming language should be NVIDIA's CUDA. And for Aurora, it has Intel GPU. So we have to use one API, which was proposed in 2019. And for Pearl Murder, it has a NVIDIA GPU, same as Summit. So we use NVIDIA CUDA. And for Frontier, it has AMD GPU. So we're using we have to use ROCm. And so it is kind of very frustrating and challenging if you want to have your application to be run on all of those supercomputers, because basically you have to provide 3 versions of your applications, which is not very cool. But if you are familiar with this area, you may know that actually we have another thing called OpenCL, but let's forget about how complicated to write OpenCL program. But if you just look at the performance between OpenCL and vendor-provided programming model, you can see there is always performance gap between them. So now the question is, do we have a programming model or programming language that I can only need to write my program once and I can compile it to make it run on different platforms? Well, there is, and the answer is OpenMP. So OpenMP is a directive-based programming models for C, C++, and Fortran, and it has been supported in most high-performance compilers, and it is supported by most hardware vendors. And so it is the most widely used high performance computing language. And there are actually a lot of real applications in different areas using OpenMP. I list some examples here. So the first one is MATLAB. I don't have to introduce what MATLAB is. And the second one is called Nifty Reg. Basically, it is a medical image registration application. And the next two are PyTorch and TensorFlow. So it is the most popular deep learning frameworks. And next one is a Blender. Blender is a sort of 3D computer graphics software that you can use it to create animated films, VR, etc. And what's more, it can also be used as a New York plate. So this is a plate. And I put two links here. The first link is OpenMP specification 5.2. It is the latest version. And the second one is some example using OpenMP. So one of the reasons that OpenMP is so widely used is it's pretty easy to make the program run in parallel. So let me show an example here. I have 3 arrays, and I want to add elements in A and elements in B and store them into C. So I write my C code in this way. I have a for loop here. If I want to make it run in parallel, basically to have multiple threading execution using OpenMP, I just need to add one line here. So it is pragma OMP parallel 4. And when I compile the source file, I just need to add -f OpenMP. And then this piece of code is going to use as many threads as possible in your system. Of course, the number of threads can be configured using some macros or using some function call to set that. So yeah. And I also put a link here. It's the LLVM support in it's OpenMP support in LLVM, because here we are using clone compiler, which is from LLVM. And I'm going to talk about LLVM later. So this talk is about GPU execution, right? So does OpenMP support GPU execution? Well, yes. So since OpenMP 4.0, OpenMP provides a new set of directive and function calls, which is a target-related directive. It can offload the computation task from host to the target devices. The target device can be GPU, can be accelerator card, can be FPGA. And we only need to do, for this particular case, we only need to write pragma OMP target teams distribute parallel 4. And this piece of code, this for loop, is going to run on a target device. Here we are using NVPTX64 as example, so it's going to use NVIDIA's GPU. And when we compile the source file, we only need to add another compiler flag, -f OpenMP targets NVPTX64. And currently, LLVM OpenMP supports AMD GPU, NVIDIA GPU. It supports NEC card. NEC card is actually an accelerator designed by NEC, and it also supports Intel's MIC architecture, so the Xeon Phi accelerators. And so you can see it's OpenMP targets. It's a plural here, right? So you can write AMD GCN, comma, NVPTX, comma, Intel, blah, 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 to make the application can run on all those target devices. And during the runtime, when the application is executed, it can load, it can based on your system, what you have in your system, and it can load the image accordingly. So the next thing is about LLVM. So because the subtitle of this presentation is SBU's contribution to LLVM OpenMP. So why would we use LLVM? LLVM is actually an open source project. It is a collection of compiler related projects. It has a clone, which is the front end that can support C, C++, Object-C, Swift, and a render script. And it also has Flon, which is the front-end compiler for Fortran. And it also has many cool projects like MLIR, which is a rising star in the machine learning world. And most importantly, it also comes with OpenMP implementation. And LLVM, a lot of vendor compilers nowadays, they are using LLVM as their code base. For example, Intel's ICC compiler, they have switched to LLVM, and AMD's AOCC, IBM's XL compiler, ARM's ARM-Clone compiler, you can tell the name ARM-Clone, so it must be LLVM based. And HP's Cray compiler, they are all LLVM based. Another popular compiler is actually GCC, and actually GCC also supports target offloading. But the performance of GCC's target offloading is much worse than LLVM's OpenMP implementation. But I want to say that LLVM OpenMP is not naturally or intrinsically faster than GCC's offloading support. It actually has a lot of people in the open source community actively working on that. And I am very lucky to be part of them and to make my contribution to the project. So in the next few slides, I'm going to talk about my contribution to make LLVM OpenMP run efficiently. But before we do that, let's first take a look at what does clone do when we try to compile a program or source file with OpenMP target offloading. So let's say we have a source file for foo.c, and the compilation actually has two passes. The first pass is a host code compilation. Basically, it's generate all the host code and to recognize the target regions. A target region is those piece of code wrapped by a target directive, like this piece of code we are showing here that is called a target region. So the host compiler recognizes those target regions and to make the preparation for the second compilation pass. And in the second compilation pass, it's called device code compilation. So it's recognize all those target regions and to emit code according to the actual target device. For example, if the device is NVIDIA GPUs, so it can emit code, it can emit NVPTX that can be loaded to NVIDIA GPUs. And as part of that, another bitcode library is called device runtime is linked into user's code. The device runtime provides some functionality implementation for those functions provided by OpenMP specification, or those functions used by compiler to implement those features to, in the user's code. So so like this piece of code shown here, the compiler will lower the directive thing into a function call, which implemented in some runtime library. And during the runtime, those runtime library actually does the actual work. So all those functionalities are provided in device runtime. The device runtime is actually for the device, and we also have host runtime, which I'm going to cover later. So after the compilation passes, for the first compilation path, we have the host object. And for the second compilation path, we have a device image. And we have an offload bundler, basically to bundle them together to make it a final object file. And this object file is called a fat binary because it contains code for host and code for device. So during the runtime, say we have an application and it's a fat binary. It depends on two dynamic libraries, libomp and libomp target. Libomp is it has all those implementations for all those features that are not for target offloading, and libomp target are implementing all those features for libomp for target offloading. Actually, there is no technical challenging or difficulty to make them into two dynamic library. It's all about a property, because LLVM's OpenMP implementation, the libomp, basically libomp was developed by Intel, and later Intel contributes their code to open source LLVM projects. However, libomp target was developed by IBM, and because of the property issue, they have to make it in a separate library. And we also have a plugin for one kind of target device. For example, we have plugin for CUDA device, we have plugin for AMD GCN, we have plugin for NEC accelerator, and all those plugins will call the actual runtime library provided by those SDKs, so CUDA SDK, AMD's ROCm, etc. So I highlighted some boxes here. So all those highlighted box means I have made contribution to them. So now let's talk about my first work. It is about concurrent offloading or concurrent kernel execution. So the motivation is pretty simple. Modern GPUs, similar to CPU actually, modern GPUs can execute multiple programs at the same time. So in order to do that, we have to make some support in the device in OpenMP. Otherwise, before my changes, before my work, OpenMP's implementation limits that capability. So there can only be one kernel running on a GPU. So when we launch a kernel, it will first transfer all the data required by the target region, by the kernel, from host to GPU, and then launch the kernel. And after the execution, it will transfer data from device back to host. And in previous implementation, if we have, for example, multiple data transfer, it will happen like this. So it will transfer the first data, wait for the finish of the transfer the second data, wait for the finish of the second transfer, and etc. And then launch the kernel, wait for the finish of the kernel, and start to transfer data back from a device one by one, which is extremely inefficient because the device is already capable to have multiple offloading operations at the same time. So in order to support that, I first made all the offload operations asynchronous. So we only need to sync for once. So the execution flow is like, for now, is like issue all the data transfer and then launch the kernel, no sync between them, and then start issue all the data transfer from device to host. And we only have one synchronization at the end of all those process. So this can save a lot of host overhead and improve the execution performance a lot. And with the multi-stream, a stream is a queue-like data structure that we can add all those commands into the queue. However, the execution of the stream operations in those streams, it is in a serial order. So if we have multiple target regions, if we have multiple kernels executing in the same time, we can push the operations for different target regions, different kernels into different streams to make them run concurrently potentially. And in OpenMP, from a user's perspective, if we want to have asynchronous offloading, so we only need to add a no wait clause into the target region. And we propose a new way to implement the new no wait clause in OpenMP. It's called hidden helper task. It's a new concept. Basically, a regular OpenMP task has to be bound to a parallel region. Otherwise, the task will be executed immediately if there is no parallel region. So we lift the restriction by separate another hidden teams of threads that is not bound to any parallel region. And for now, it is only responsible for executing those target tasks. And a similar concept is being discussed in the OpenMP committee, and it is expected to be released to be part of in OpenMP 6.0. And we also, in order to improve the dependence resolution, because maybe we have multiple kernels and maybe one kernel access data that is touched in another kernel. So they have some dependencies. In order to improve the resolution of the dependence, we lower all the dependence resolution to the target device side. So in this way, all the kernels, all the target region execution, they don't have to come back to host to resolve all the dependencies and then start to execute the kernels on the device back and forth, which can also save a lot of overhead. And in our benchmark, we can show up to 6.5 times performance improvement. And Mini QMC, which is a proxy application of QMC Pack, is using this feature. QMC Pack is a more than high performance open source quantum Monte Carlo simulation code. And basically a proxy application is to extract all the core computation from the real application and to make it very simple to be compiled and very developer friendly, because it doesn't have to have all those dependencies, same as a real applications. It is very developer friendly because we can use those proxy application to optimize the compiler and runtime, and we can evaluate our optimization using those proxy applications instead of using real application directly, because real application sometimes or most of the time is really hard to compile. And Mini QMC Pack is using, and also QMC Pack is using this feature. And all the feature I mentioned above has already been LLVM 12, and I have upstreamed them. And I just got to know that Intel's latest OpenMP compiler adopted my implementation as well, and to make it part of their Intel's compiler, because Intel compiler, like I said before, it is LLVM based, so it can easily adopt my implementation. So this work was published in LCPC last year. And the next work is about memory optimization. So when I evaluated my implementation for for this work, I found out that a large amount of host side overhead is wasted on repeated device memory allocation and free. So we all know that device memory allocation and free are very expensive. So in order to tackle this issue, so we buffer. I implemented a memory manager, and it can buffer all those small target memories. So when the memory is not used anymore, it is not freed to the device directly. Instead, we buffer those small amount of memory. And next time when we have a request of memory, we will first check if we already buffer that size of memory. If yes, we directly use that. In this way, we don't have to allocate the memory on the device as well. So furthermore, we also pack small first private variables and to issue the data transfer from host to device all at once. The reason behind this is issue data transfer also has host side overhead, and if we can, of course on the one side is the real execution of the data transfer depends on how much memory we are going to transfer, of course. But it's also, for sometimes in users application we have a lot of small size of memory, and they are all actually only read on the device. So first private variables in OpenMP's perspective, it is those variables that is only have to be transferred from device from host to device. They are not required to transfer back to host after execution. So those kind of variables are usually used in the kernel to just for read the value from them. So we pack all those small variables and to make it in a data structure, and then we transfer them all at once to save a bunch of overhead to issue the data transfer. So Grid Mini, with our optimization, Grid Mini obtains significant performance improvement. Grid Mini is a proxy application for Grid. And Grid is an application that's for lattice quantum chromodynamics application. And so it's a new lattice QCD C++ library. And this figure was from one of our colleagues from Brookhaven National Lab. And you can see that the red bar here, which marked patched, is the code with my optimization. And the green bar is for CUDA. So with my optimization, we can see OpenMP's version can have same performance as CUDA's code, CUDA's version. And without my application, without my optimization, the green bar, the blue bar show here, it has a large performance gap between them. So this optimization has already been merged into LLVM, and it's available since LLVM 11.0.1. So next work is about OpenMP GPU device runtime, or we call it runtime library. The device runtime is actually here, like I shown here. So it provides those functionalities in OpenMP specification or for compiler generated code. The device runtime in LLVM OpenMP was initially developed by IBM targeting CUDA device. So it was written in CUDA. And later, AMD adapted those code to separate the implementation into two parts, target dependent part and target independent part, and to make target independent parts a common part, and to mark all those target dependent keywords. For example, the __ device is CUDA keywords to wrap all those keywords into a macro, and those macros are defined in target dependent implementations. And when it is compiled for CUDA device, it is compiled as CUDA. And when it compiles for AMD device, it is compiled as AMD's heap. So this mechanism works, I would say, pretty good. One of the reasons, or the only reason that it can work, is heap really resembles CUDA. So if in the future we have another target device, and if the corresponding programming language doesn't resemble CUDA, it's not gonna work, or it is not that natural or direct to make it work. So the question comes to us is, can we write the device runtime in a common way that it can be compiled for different targets, and we don't have to implement them in vendor provides programming models? And yes, like we said before, OpenMP compiler can already recognize the code for target region, the code of the target region, and to emit corresponding code that can be executed on the device. So if we can tell the compiler that, the OpenMP compiler that, okay, that piece of code is for the target device, and we only read the device version of the code. So we only need to invoke the second compilation path we mentioned before to compile the device code, and then we can get a valid device runtime, right? So that's how we did it. So we rewrote the device runtime purely in OpenMP, and no more CUDA, no more heap. In order to do that, we mark all those the code that will be executed on the target device using OpenMP feature called OpenMP declare target, and all those codes wrapped by the directive will be taken as device code, and the OpenMP compiler will generate the device code for that. And another advantage of this is we don't require vendor toolkits or vendor SDKs to build the device runtime, which actually created a pretty large barrier for those Linux distribution package managers. So if before, if you just using, for example, apt install OpenMP on Ubuntu system, right? The OpenMP installed doesn't support target offloading out of the box, because because the build of the device runtime has to have those SDKs installed on the device on the system, which sometimes is not possible for those package managers. And after we rewrote the device runtime, we compiled we compare the code generated by our version and generated by the previous CUDA or heap version. We see we can tell that the same device code is generated. And we also extend the OpenMP specification to add some new features into that have not been in the spec yet. And we also implement some missing features in current LLVM OpenMP to make the whole thing work. And it has been already available. Most of the part has been already available since LLVM 12, and I already upstreamed them. And it also makes a lot of more things possible, and I will gonna to give some example later. So this work was published in IWOMP 2021. So now let's talk about one use of the OpenMP device runtime. New version of the device runtime is called host offloading. So we already know it's really hard to develop code for GPU execution. And it is even more challenging to debug it, because no one can make sure that their code will not have any bug and it can be compiled and run very good without any debug. But the debugging is kind of very horrible. One of the reasons is many tool chains that are available on host, but don't support GPU. So we implement a host offloading. So basically it is a GPU simulator that can run OpenMP target offloading code directly on host, on CPU. It has all those features provided by the target device. For example, it has thread blocks, it has warps, it has all those grids, different concepts on the device. And we are using the same compilation tool chain to compile the host code offloading code. And the most important thing is it run on host, and we can use all the host side debugging tools to debug the code. I put two examples here. The first one is to use debugger. It's LLDB or GDB that can debug the code. We have the reference of a null pointer here. And we also have, we can run the thread sanitizer to see if we have memory leak or have some data risk in the code. And we are working on the upstream for now, and the corresponding paper was published in LLPP 2021. Okay, so the next thing is about OpenMP aware optimization. Because like I said before, OpenMP was initially designed for host execution. So it has a lot of, it supports a lot of computation pattern that is very efficient on host, but extremely inefficient on target device. The traditional compiler optimization passes, they cannot optimize those kind of code. And we have to have OpenMP aware optimization. And so that's why we have that. This is actually a collaboration with a bunch of people in different national labs. We have people in Oregon National Lab, Oak Ridge National Lab, Lowell Livermore National Lab. And I'm responsible for one of the party in that. So this figure shows the performance improvement in different kind of benchmarks. We have access benchmarks, we have RS benchmarks, SU3 benchmark, mini QMC, and those benchmarks, like I said before, they are all proxy applications, and they extracted from a real-world application. XS Bench and RS Bench is from a project called OpenMP. It's a Monte Carlo, Newton, and the Fulton transport simulation code. SU3 Bench is a lattice QCD matrix multiplication, and it is core routine for a lattice QCD code. Mini QMC I mentioned before, is a QMC pack. So the baseline here is LVM 12, and we have different optimization. We have heap to stack. We have Rtc Spec, which is the part I was responsible for. Rtc Spec stands for runtime call specification. So the idea behind this is we can actually deduce some runtime information during compile time. So let me show you an example. So in this figure, we have a thread limit 8 here. So it tells OpenMP that I only want to have at most 8 threads for one team, because for grid mini, 8 threads can give the best performance. And we tell those we write the thread limit 8 into the code, and during compile time we can read that. So we know that, okay, user only want to have 8 threads to be in one team. So we will only create 8 threads for a team. So now we know that no matter what happens, we will have 8 threads during the compilation, during the runtime, right? So there are some routines or some function calls in OpenMP to query how many threads that I have during the execution, during the runtime. So we can fold the function call directly to directly replace it with 8 in this case. So we don't need to have a function call in this case, right? So similarly, we have we can deduce the execution mode, because OpenMP supports 2 execution modes, SPMD mode and generic mode. Generic mode is like those host versions, the OpenMP code for CPU applications. Most of them are actually not very efficient on target device. And SPMD mode is the most efficient way to implement GPU applications. But OpenMP both support that. So during the runtime, we have some mechanism to support different modes. So we have to query whether it is SPMD mode or generic mode. So if we can already deduce that user's application, in this application, we only have SPMD mode kernel. So no matter what happens, it is always SPMD mode. So we don't have to actually call that function to query what mode it is. So we now know that it is SPMD mode. So we replace that with SPMD mode directly. So same thing applies to thread execution and launch parameters. And we can see with our optimization, we have pretty good performance improvement compared with baseline. And for some applications, for some benchmarks, we can even have the same performance as CUDA version, which is the purple one and the red one. So for XS Bench and RS Bench, we have pretty good performance. And this work has already been accepted by CGO 2022. So next work is about a re-implementation of the device runtime. So before I said I rewrote the device runtime purely in OpenMP, right? So I just rewrote it in a different language, but I didn't change the logic to implement it. But when we evaluate this paper, we found out that we cannot optimize some piece of code because of the poor design of the previous device runtime. In order to further optimize the code, we redesign the device runtime. the core idea behind this is you only pay what you actually use. So this figure shows an example. So in the device runtime, we have initialization, and we also support the debug output for the initialization such that user can know what's going on during the runtime. And we also have work sharing support. We have nested parallelism, but users' code may not use all of those features, right? So if users' code don't use those features, ideally, they should all be optimized out. So, but it is not very easy to do that because in the implementation of the device runtime, there are some function call. And there is one kind of optimization is called constant propagation. Basically, if we already know the value of a global variable or just a variable, and if we can deduct that that variable is not modified in all of the later execution, we can directly replace all the read of the variable with the value, right? But there is some function call in the device runtime that we call it has some side effect. So a side effect is the function call may change the status of the variables, those variables. So the compiler, if the compiler cannot prove that, okay, that function call doesn't change anything. So if the compiler cannot prove that, the compiler cannot replace all the values after the function call with replace all the values. So in order to make the compiler smartly replace all those values to make the constant propagation, when we have to do something when we implement the device runtime. So this is also a collaboration with a same group of people as previous people, and I am responsible for the implementation of the device runtime. So we are using more than C++ and the pure OpenMP 4.1 code for the device runtime. And in order to make the optimization work, we add a lot of features into user's code, into the device code runtime to guide the compiler to optimize that. And we also propose some optimization in this paper, in this work. And we also support a totally new work sharing mechanism in this version. So this figure shows the performance improvements for different benchmarks. So you can see XS bench, RS bench is our old friend, and it also has a test snap is a proxy benchmark of a snap application. Snap application is a fourth calculation in labs. It's for a molecular dynamic package. And we also have a mini FFM, which is a benchmark developed by University of Bristol for fast multiple method to solve Laplace equation. So with our optimization, so we have different versions. We have the new device runtime without any optimization. We have a new device runtime without any assumption. The assumption is that piece of code that I mentioned before to guide the compiler for more optimization. And we also have a complete version. So if you look at the performance, the new device, the bare new device runtime, the raw new device runtime, it's in some cases it's even worse than the old device runtime, right? The reason is many optimization designed for the old device runtime doesn't apply to the new device runtime easily. So we didn't adapt those optimization to that. So in some cases it is worse. And for mini FMM, because one of my implementation bug in that it has a data race in that, so it directly has a runtime error. But with our assumptions and add our optimization, you can see the performance improvement, different performance improvement in different cases. And for some version, it can even better than CUDA version. And part of the implementation has already been since LLVM 13, and at least the device runtime, which the part I was responsible for, was already available since LLVM 13, but the optimization was not in is not in position yet. And we submitted this paper to IPDPS next year, and the paper is still under review. So the last work I'm going to mention is JIT support. JIT support stands for just-in-time compilation. So all those compilation I mentioned before is called ahead-of-time compilation. So it generates the device code, generate a binary device code that can be executed on the device directly. So instead, we can actually generate that piece of code during the runtime, right? So Java is a typical example of just-in-time compilation. So Java compiler basically just to generate a file called a class file. It's actually a middle and IR intermediate representation. And during the runtime, the IR will, the class file will be loaded to Java virtual machine, and the Java JVM will just generate code, the actual code to during the runtime. And we also, OpenMP, at least the specification doesn't support JIT compilation. So we add this feature into OpenMP. The reason is also very simple. So there is always information, runtime information that we cannot know during the compile time. If we want to further optimize the user's code, we have to know the runtime information. So JIT is the best option here. So in this work, I add the basic JIT support in OpenMP. So during the compilation time, we only embed intermediate representation into the binary. And during the runtime, the IR will be loaded, and with the device information, with all those runtime information, it will generate the actual code that can be executed on the device. We also provide some optimizations because we now have more information. So we have to add some more optimizations. We have specialization. Basically, the specialization is, for example, for a kernel argument. For those arguments, if it is a value, we can replace the value. And we only have specialization for read-only global variables. And we also have a launching parameter. For example, if we can know, because sometimes we don't know the number of threads or number of teams during compile time, so we cannot fold the function call during the compile time. So now we have all the information, and we can fold those function calls. And we also have pointer alignment. Because each target has a default value of the pointer alignment, and pointer alignment affects the code generation very much, especially for vectorization. In order to generate a more vectorized code, pointer alignment is one of the key factors. So if we can know the pointer alignment is more restricted during the runtime, we can have more aggressive code generation. But JIT also introduced a lot of host overhead, right? So though we have a more efficient kernel for the device, but we cannot ignore the overhead introduced on the host. Then we proposed and we designed a very fine designed multi-level caching system, such that if you look at the program's overall execution, the host overhead is really small. We have some preliminary results. So SU3, it has a 25% performance improvement. XS Bench has 9-ish improvements, and Test Snap has 12. Mini FFmpeg has 25. And one of the spec benchmarks, spec ACC Excel benchmark, post-stencil have 3 times performance improvement. And we are going to submit this paper to CC 2022. And actually, we supposed to do that on Monday, but the deadline was extended for almost 1 month, so we can still do more things. So now the last thing is I'm still working on that, but I have not done yet, is about the heterogeneous IR module. I just going to briefly introduce that. So all the optimizations I mentioned previously, they are doing separately. Basically, I first optimize host code, and then I optimize the device code. But sometimes we need the information from host code to optimize the device code, and vice versa. But it is not possible to do that. So we propose a heterogeneous IR module that can merge the host code and device code into a same module, into one module. And we optimize the code directly in the module. And if this is quite challenging because it requires the changes in the core LLVM. But if I can do that, it can benefit all of those heterogeneous programming models, no matter CUDA, no matter RACOM, SQL, OpenMP, you name it. I'm still doing it, so hopefully I can get some results pretty soon. So yeah, that's pretty it. I have contributed more than 150 patches in the past 1.5 years, and all of them have already been available in LLVM. And if you have any questions, and if you want to use OpenMP target offloading for your code, or if you already have that piece of code and want to write it, run more efficiently, feel free to contact me with the email I showed here. So yeah, thanks.
Hi, Shilei, can you hear me?
Yeah.
Oh, great. Okay, I wasn't sure. So I had trouble finding a place where I could be quiet. So I spent most of the time listening on the phone. But I knew your slides, so that wasn't a problem. Okay. Yeah, thank you very much. So I wasn't going to ask a question. I just wanted to make sure everybody knew I was here. And as I think you can tell, Shilei has been incredibly productive. When we started working on LLVM, it was a very slow compiler, and it's obviously it's been a community effort, but Shilei has played a very big role in improving its overall performance, as well as adding some new features. So it's been quite exciting. Okay, so I guess just back to the others and for questions. It's just a couple minutes left, right?
Oh yeah, sorry for the long talk.
Hey, Shilei, thanks very much. Robert Harrison here. I'm sorry I was late joining. I was actually walking past the small conference room and I heard you presenting and I thought, I recognize that voice. Anyway, so I rushed back. And anyway, so the optimizations that you're putting in the runtime right now, how relevant are any of those to task-based computing, or is it really agnostic? I mean, is a parallel loop basically just turned into a bunch of tasks, or is it more complicated than that?
So for now, we optimize for mostly optimize for device execution. So yeah, that's why we have an OpenMP aware optimization. So it's basically optimized. It look up all the codes running in the device and to optimize them to take the characteristic, to take the target the architecture difference between CPU and GPU into consideration to optimize that, right? But the task is actually kind of a host concept. So okay, yeah, so we don't have specific code for that particular thing. But
so
yeah.
Let me just ask for that to be clear. So that there's no concept of offloading a task to a GPU. It's basically a loop that you're offloading.
Right, but it is called a target task for sure. Okay. But from the GPU's perspective, it's just a kernel.
Okay.
So it will not have some like task scheduling. But we do have a support, at least the task support in GPU. But for now, the implementation is just ignore the task directive.
Okay.
Yeah.
Well, let me ask another quick question while other people are being quiet about LLVM itself. And I think as Barbara commented that, but going back, I think just a couple of years, that LLVM support for OpenMP was was limited. What can you say about the roadmap for LLVM? Does that community have a sense of direction for OpenMP and I guess HPC support in general?
Roadmap of at least currently we are actively implementing all the new features because OpenMP 5.2 was just released. So we are actively working on those features in that, and we also propose more optimization to LLVM OpenMP. Currently, one of the key features is the reduction support. So we reuse all the old reduction implementation. It's buggy, it's crappy. So we want to have a new implementation of that. And the OpenMP 6.0 features, especially some being discussing. One of them is the hidden helper task I mentioned. It's already been in LLVM for now. So yeah, there's something like that.
Okay.
But the goal.
Yeah, so sorry, you could. Yeah.
Oh, sorry. The goal is actually to have more features, at least supported in LLVM. Yeah.
Okay.
Yeah, I was just filling a gap, but as to say, the OpenMP efforts are pretty well coordinated. So it's very active.
Well, an amazing amount you've accomplished there, Shilei.
Thanks.
Well, let me sneak in with another question. So I end up working a lot with people on the runtime side, basically because languages, parallel programming models that are essentially all library based, right. And so having a compiler that you can use to do these transformations is huge. And in particular, I was struck by what you were doing with the thread local data and you bundling that basically for efficient transfer to the GPUs.
Yeah.
And what's actually happening there on the back end? I mean, how much of that is sort of static analysis and how much of it can you do at runtime?
We have those information, what kind of the variable it is. We have that information during the compile time. So we already have that information, but we don't do that in the compiler. During the runtime, we will also have the information, because during the runtime we can know the address of those variables, right? So we can bundle them together. But it's not very easy to make it happen in compiler or to generate a code directly to bundle them together.
Okay, so you can't sort of like magically pre-allocate everything so it's a contiguous block, right?
Right.
Okay.
That's the reason we chose the first private variables, because we don't have to transfer them back to host and to have a buffer and then to copy from the buffer to the actual variable, because in that case the overhead will be very much.
Okay.
Yeah. But we do have some compiler magic to bundle the arguments to when we call a parallel region. We do have that optimization, but it is still being developed, and yeah, it's already on Fabricator under code review. It has been tried to launch for many times, but every time we launch it, there will be people complaining it breaks something, then we have to revert it. But yeah.
So I was curious whether anybody on the call is using LLVM with OpenMP.
Well, I mean, certainly I am, and I'm not using it on GPUs, and there's lots of people on Okami using it, mostly through ARMS compiler. So that's LLVM 11 based, not 12. And LLVM 11 suffers that it only had support for, I think, for OpenMP 3.1 or something.
Right, yeah. Yeah, I'm not sure why some of the ARM changes too are not yet back in the main trunk, but
I've had long conversations
Find out.
with John Linford about
Yeah.
that. He complains that for whatever reason, the community is not accepting the stuff they're pushing upstream. And so he claims
Mhm.
ARM doesn't want a commercial compiler, at least in the HPC space. They want it all to go into open
Mhm.
source. But the problem is getting it pushed into open source.
So when we first started with OpenMP, which was quite a while ago now, we had exactly the same problem. And at the time, I think there were people in the LOB community didn't care enough, which would surprise me though with SVE. So, but sometimes it's a matter of getting somebody's attention. So I don't know who they've been interacting with, but maybe we can find that out.
Yeah, that would be
It would
huge.
be very nice. Yeah. Yeah.
Shilei, I'm sorry to co-opt your talk briefly here, but Ava's going to give a presentation in the ARM buffer SC this afternoon, and one of the major findings there is really this huge gap in performance between the proprietary software chains and the open source tool chains. And of course, the open source tool chains have a tremendous advantage in support for modern languages.
Yeah.
Okay. Okay. I'll see if I can make it. Yep. Thank you. Okay. So I'm not sure. I think our time slot is over, right? I had 11 to 12. Is that correct?
Yeah, it's probably time to wrap up. So
yeah. So I don't know if there are any last minute questions. So. Okay. Sorry, Rob.